Welcome to EDU World Space.
Okay, in this problem, we're asked a lot of questions concerning a concave mirror with a focal length f, and we have an object located some distance greater than f, which will of course result in a real image. So to start us off, we were asked to prove that the magnification m is equal to f over f minus d naught. We're then asked to sketch what m looks like for varying values of d naught. And we're asked to find the point where m equals 1, where the image height and object height will be identical, so there's no magnification at all. And we're asked to find some general region where m is much greater than 1, resulting in a big amount of magnification. So to start us off, we're going to be making use of the definition of magnification. M is equal to the ratio of heights, but it's also equal to the negative ratio of distances for the image and object respectively. With that said, we can write the image distance as negative m d0. We can now combine this with the ideal lens equation. 1 over f is equal to 1 over di plus 1 over d1, or di. 1 over d0 o is equal to 1 over di for object distance and image distance. We can replace the image distance di with our result we just derived. So we can recast this as 1 over do plus 1 over minus m do. And doing a tiny bit of algebra, tiny bit more, we get m equals f over f minus do. So that's the result we're looking for. We got it. So if we simply set f to be some number and always have do greater than f, when we plot this thing, we will end up with a plot that looks something like this. Probably should plot it this way instead. Okay, so here's m, here's do. We end up with something like this. Okay, so we have negative values of m, and they get larger in magnitude as we get smaller and smaller values, or values approaching our focal length, which we'll have right here. So we have an asymptote happening. And this is our plot. And you can show it just by plotting this for some real value of f. It's hyperbolic in a way. Now, to finish this off, we need to find the point where m is equal to 1, indicating no magnification at all. We can do that very simply because m is equal to f over f minus do. Set it equal to 1. Thus, do is equal to 2f. And for f of 45 centimeters, it must be 90 centimeters or 0.9 meters. Okay. And lastly, just by looking at the graph qualitatively, we can definitely say that to get an image that's much larger than the object has to be at a point just beyond the focal length, because we have some hyperbolic behavior. So for m to be, the magnitude of m to be much, much greater than 1, d naught must be approximately the focal length, just slightly beyond it. And that's pretty much everything we can answer.